not saying basis, you have a weaker notion called sub-basis. And there in the sub-basis definition, you don't have to put this. Okay? It is enough if you just say this. And then the topology generated by sub-basis will not simply consist of unions, but you allow yourself finite intersection of members of your collection S. Okay? I will not write it for want of time, but we will have occasion to encounter it later. Okay. So notion of sub-basis, but I am not going to, I just said it in words, I am not going to write it down. Alright. Anything else? Yes, there are, the moment you say things in this manner, immediately certain questions come into picture. Okay? But these questions you will not see in the textbook right after this, maybe several chapters later. For example, I give you a topology, namely, let us say just the median one, topology on the real line given by intervals, open intervals. Okay? You just take that. Question, can I find a basis for it which is as small as possible, in the sense that it contains only countably many members? Now see, my collection B, this is enough for me to generate auto open sets. Alright, how small can I choose it? How small can I have the collection? So, small in what sense? Think into the cardinality. Can I find, given a topology on a space, can I find a collection basis which has only countably many members? Countably infinitely many members, or at most countably infinitely many members. Okay, sometimes it is possible, sometimes it is not possible. And if it is possible, you say that the topological space is second countable. Example, real numbers. There you don't have to take all possible open sets A, B, A and B real numbers. It's enough if you just take A and B to be rational numbers. Okay? Because, well, any open interval A, B, suppose A happens to be rational or B happens to be rational, you can still express it as a union of open intervals where both endpoints are rationals. All you need to, you understand? So, here is my interval A, B. It could be that A is root 2 and B is some 2 root 3. It is then not in my collection. In my, what is my B? My B is only those open intervals where both endpoints are rationals. Okay? But I still want to say this generates the same topology as the ordered topology or arithmetic topology. How will I do? It's enough now to check that any open interval can then be expressed in these terms. So I take an open interval like this. If both endpoints are A and B, both are rational, then it's already there in my PD. I don't need to worry. But suppose it's not. Suppose A is irrational. Then I find a sequence of numbers A n which converges to A. And similarly, and each A rational number. It is possible, I know that, because of density property for rational numbers, it is possible. Similarly, I find a sequence Bn, increasing sequence, here distinctly decreasing, here distinctly increasing, and converging to B. Okay? And Bn, they are all above A, Jn's are all below B. You can arrange on them. Now write A, Bn, and write Bn. And now, since these are in my basis, union will also be in the topology. May not be a basis element, but it's in the topology. But this is same thing as A, B. In fact, this, in some way, this trick was used to show some property in the previous lecture towards the end. Okay, so you see, it's good to have this property. Having said that, I should now give you an example of a space which does not have this property. Right? How are we doing in terms of time? Fine. Okay. So with the next example, let us start this. So consider RL. Now what was RL? RL was the topology in which I can say now basic open sites are one side closed, left side is closed, right side is open. This topology, so these are the basic open sets. Okay. So a set here is open, you can only express the union of these things. It is not second order. Now the previous trick of taking both endpoints rational will not work. Okay? Because if I just make this closed, something like root 2, 3 or something, I cannot write it as a countable union of intervals, even semi-closed, inside closed, with only rational endpoints. Well, this is not an entire proof, but you will see that it is simply not possible to do that. Okay? There are a few other related concepts. Yeah. Having talked about this one, let me say this following thing. I also talked about the rational number. See, some notion of density. Consider this set to contain Rn. Okay? So I am just looking at rational numbers in RL. In R we all know it is dense. Okay? See, the notion of dense etc. depends on the topology. If I change the topology, then everything is changed. Okay? So everything depended on the notion of topology. Now I have changed the topology here. So rational numbers is contained in real numbers. Okay? Question, is this dense or not? Is Q dense? Okay, maybe I will stop here and let you think about it. We will pick it up. We will answer this in the afternoon session. Okay, we'll stop.
Measure. So we say that Fn converges to F in measure if for every epsilon positive limit n tending to infinity, the measure of ZFR x is that mod Fn x minus Fx is bigger than equal to epsilon. So yesterday I introduced this notion of a characteristic function, chi e of x equals 1 if x belongs to E, 0 if x is not E. So now I am going to define a sequence of functions, the following. The first function is chi 1 1. This is chi of 0 1. It is 1 on the whole interval. Next, I am going to divide this interval into two parts, and I am going to define the characteristic function of this interval is chi 2 1. The characteristic function of this interval is chi 2. That means the function is 1 in this half, 0 here, or 0 in this half and 1. So next I divide it into 3 equal parts. If it is 1 here, that is chi3 characteristic function. Characteristic function of this part is chi3 2 and of this part is chi3. So general, I will divide it into n equal parts. Okay. What are the points of division? I minus 1 by n or I by n, where 0 less than equal to I less than equal to n. If I am dividing 0, 1 into n equal parts, what are the nodes at which I will divide? It is I by n, where I equal 0, 1 by n, 2 by n, 3 by n, up to n by n, which is 1. So I will define chi and I as chi of I minus 1 by n, I by n. So it is the characteristic function of the ith interval when you divide it into n equal parts. Okay. So look at the sequence. This sequence does not converge at any point. It is not a convergent sequence pointwise. Why? Take any x. If I divide it into n equal parts, then x must lie in some of one of those. Okay? That alone will be 1 and the other case will be 0. So however far you go for every n, so chi1 1 of x will be 1. One of these will be 1, the other will be 0. One of these will be 1, the other 2 will be 0. One of these will be 1, the other rest will be 0 and so on. So however far you go, there will be a 1, there will be zeros. So such a function is oscillating between 0 and 1. So it cannot converge on any point. Okay. So this sequence does not converge pointwise. Is it fair to? Okay. Now if you take measure of the set of all x such that mod chi and I of x is greater than epsilon for some epsilon positive. Where we have epsilon. When can this happen? Only when chi and I takes the value 1. Because these functions take the value only 1 or 0. So if it is bigger than epsilon, then it must be the value 1. Where will it take the value 1? It will take the value 1 in this interval. What is the length of this interval? 1 by n. And what is the limit as limited state will be? 0. So it satisfies this condition. So chi n converges to 0. So this sequence converges to 0 in measure. So it does not converge pointwise anywhere, but it converges in measure. That means it is 0 almost. Where it is not 0, where it is bigger than epsilon, is a very small set. But it is not a set of measure 0, but it is a set of positive measures, but as small as you like. Okay? So this is convergence in measure. So now we want to examine the relationship between pointwise convergence and convergence in measure. So this example tells you that in general you cannot expect anything. So what can you expect? Proposition. Assume mu of x is finite. Then if f Fn converges to F almost everywhere. That means except on a set of measures 0, it is pointwise convergent. Then Fn converges to F. So let us take D to be the set of all x, such that f and x does not converge to f of x. So yesterday we wrote contrapositive statements all the time. So let us now say what this means. This means x is in D if and only if there exists an epsilon positive such that for every n there exists an m bigger than or equal to n such that mod fnx fmx minus fnx is greater than 1. This is what we mean by saying Fn does not converge to f of x. This is correct. This is what we wrote yesterday, contrapositive. So now I am going to write this in terms of set theory. There exists an epsilon positive. So I am going to put union over epsilon positive. There exists means some epsilon is there. So when I take lots of sets with some epsilon property, there is at least one of them. It's in at least one of them. That means it's in the union. Such that for every n, so I take intersection n equals 1. There exists an m bigger than n. So union m equals n to infinity. Em of epsilon, where Em of epsilon is set of all x such that mod Fm of x minus Fx is greater than 1. So this statement which I have written here is identical. Now what is this shape? This is nothing but lim sup of Em epsilon. This morning I defined lim sup of sets, lim for sets. Please look at the definition. Now D, what do you know by the hypothesis? Fn converges to F almost everywhere. This is the set where it does not converge, so 0 must be equal to measure of D. Now D is the union of so many things. So for every epsilon positive, this is bigger than or equal to lim sup En epsilon. D is the union of all epsilons. So for every epsilon, this set is bigger than what is inside, and so the measure of this set is bigger than the measure of that set. And this morning I gave you an exercise. This is bigger than the limb suit of EM, measure of EM. And that is possible because μx is 5. Because in the exercise this morning I said I wrote down 2, one for limb in, one for limb suit, and in the question I gave for limb suit I said you need finite measure because somewhere you will do some subtractions. So limb suit of EM epsilon is less than or equal to 0, but limb suit is all Poisson measure. Limb suit is always bigger than or equal to limb in. So limb in of En, measure of En epsilon. But measure is always non-negative. So limb suit, limb in, shape in is 0. This means that limb suit equals limb in equal to 0. That means En epsilon converges the measure. So that is mu of En epsilon goes to 0. The limb suit is 0, limb in is 0, then the limit is 0. That's how you define convergent sequences in terms of limb suit and limb. But that is exactly the definition of convergence equation. That is Fn converges to F. So if you have the finite measure space and you have convergence almost everywhere, then it implies convergence in measure. Now about the converse. If you have convergence in measure, can we have convergence almost everywhere? Well, this example says no. But if you look carefully, I can choose a subsequence of this for which it converges. Because I will only choose those i's for each n for which it is 1. Then that's a constant sequence 1, that's a subsequence which converges to 1. Or I can choose those i's for which it is always 0, it will converge to 0. So there is a subsequence which converges. Okay? So that we will try to prove in general. For that, there is a very useful result. Let Ek be a sequence of measurement sets such that sigma mu of Ek is convergent. Very simple criteria. So take a sequence of sets such that the sum is a convergent series of the measures. Okay? Then except for a set of measure 0, every point x belongs to only at most a finite number of the sets. So you take x and see how many EKs it lies. Well, it may lie in a finite number of EKs, or it may lie in many EKs, infinite number. Now, the set of all points where it lies in an infinite number of EKs will be a set of measure 0. That is what we are going to say. If the measures is a convergent series, then every point except on the set of measures will lie only in a finite number. So let's see how this works. So let us say x belongs to infinitely many t. What does this mean? That is, for every n, there exists a m bigger than equal to n such that x belongs to Pn. Do you agree with this or you don't? If x has to lie in infinitely many k, however far I go, there will be a set beyond that where x is. Remember? If it lies only in finitely many, then if I go far enough afterwards, it won't be there. Won't be a member. Now let us write this in set theory. This is nothing but intersection over n equals 1 to infinity for every n. There exists a m bigger than n. So union m is n. So E equals this. That means E equals this. Just few symbols, then things become very clear. Sometimes the other way around, but then so E equals this. So mu E is mu of all this, but it is the intersection, so it is less than the measure of any of these sets here. So less than equal to mu of union m equals n infinity em for all n, which is less than equal to sigma m equals n to infinity mu of n. For all. What do you know about sigma mu e? It's a convergent series. So the tail of the convergent series can be made as small as you like. So you can always find, given any epsilon, this will be less than equal to epsilon for n large. So of course 0 is less than equal to mu e. It is less than any epsilon positive. So mu e has to be 0. So this is the Borel-Cantelli lemma. So now let us use it to prove the converse of this, or partial converse. Fn converges to f in measure, then there exists a subsequence which converges almost. So proof. So without loss of generality, we can assume f equals 0. Otherwise, you work with Fn minus f. That's all. So Fn converges to 0 in measure. If you don't like this, whenever I write Fn, write Fn minus f. E and M equals to for x such that mod Fn of x is greatly equal to 1. Define. Then what does it mean to say convergence in measure? The limit of this as n tends to infinity is 0. So mu of E and M goes to 0 as n tends to for every. That means there exists a n naught of m such that for all n greatly equal to n naught, measure of e power nm, it goes to 0, so it will remain less than any number I like. I am going to take less than 1. That is my epsilon. So in particular, mu of E n naught m comma m is less than 1/4. But what do you know about sigma 1/2 power m? The geometric series converges. Therefore, sigma mu of e power n naught m also converges by comparison. Okay? So now apply the Borel candle. What does it tell you? Except on a set of measure 0, every x belongs to only finitely many E n naught m. Yeah, it will be clear in a moment. So, why Borel cantilever? Except on a set of measure 0, every x belongs to at most finitely many E n naught m. There exists a capital M such that for all m greatly equal to capital M, x does not belong to E n naught m. Okay? It belongs to at most finitely many. So after some time it won't be there. But what does this mean? That is, for all m greater than capital M, f n naught m of x is less than, because it is not in this set. That is, f of f n naught m converges to 0. But it's except on the set of measure 0, so on. So I have found a subsequence which converges almost everywhere. So convergence in measure implies convergence almost everywhere for a subsequence. Okay, so now, so X is a set S a sigma algebra, mu is a measure. This is called a measure space. This is a set. This is sigma algebra. And this is a measure. Suppose we have a simple function. What is a simple function? Phi equals sigma I equals 1 to n alpha I chi of ei, where ei belongs to S. And without loss of generality, we can assume ei's are disjoint. Because if they overlap, yesterday itself I said, we just break it into disjoint sets and add the values on the overlap. Then you define integral phi d mu over x. This is the notation. Integral of phi over the set x with respect to the measure mu. Okay? That's how you read this notation. Integral phi d mu over x to be what we said yesterday, 1 to n alpha I. Multiplying the value by the length of the